Pre-calculus students, welcome to your 4.8 notes. Today we're going to take a look at applications and models of trig functions. We're going to start out with a little bit of review, and then we're going to move to some brand new stuff pretty quickly. So let's get right to it. One of the most basic things we use trigonometry for is the solving of right triangles. So let's start. Now most of this will be review to you, but let's go ahead and refresh our memories on how we solve. There are kind of two different types of right triangles that we solve, and one of them, we obviously know the right angle. We know one angle and one side. It doesn't matter which side it is. It could be any side. But let's start by finding angle B. We know that angle B is the rest of the 180 degrees for the triangle, or even simpler, if you just look at the two acute angles, you know they have to sum to exactly 90. So angle B here would be 53 degrees. That's pretty fast to find that. Now what we're missing are the two side lengths, of course. And so I'm going to start by finding side B. Notice the notation here. When you use capital letters like capital A, capital B, capital C, that represents angle measures. Lowercase letters like in a lowercase a, b, or I'm going to call the hypotenuse C, those all represent side lengths. So if I want to find side B, I can just simply look at the angle that's given to us. I know the side of 17 is here, and then side B, the function that connects those would be the tangent function. So the sine of 37 degrees, the tangent of 37 degrees is equal to 17 over B. Now when you punch this in your calculator, think of it as multiply both sides by B, divide both sides by tangent of 37, and you will get your answer. Do remember that since we are working in degrees, you need your calculator to also be in degrees. And it does say in the instructions to round to the nearest hundredth, so we'll do that. And then one more computation to find the hypotenuse. I'm going to do the sine of 37 degrees is equal to the opposite side divided by the hypotenuse. And it's really kind of the same thing we do here. 17 divided by the sine of 37, and we get our missing side. This hypotenuse is about 28.25. Now some of you may have said, well, hey, Mr. Hale, what if I just use Pythagorean theorem once I know two sides? Totally fine. The only risk involved is if you made a mistake on the first step, you'd compound it, but I think you guys can handle some basic trigs. So if you'd like to use Pythagorean, you just go on right ahead. Let's take a look at number 2 then. On this one, we know we have our right angle, and we know two of the sides. Okay, so we can actually find the third side pretty easily, Pythagorean theorem. And you may recognize this one. It's a pretty common Pythagorean triple. E squared plus 15 squared equals 17 squared. That E, it's kind of weird to use E. It's not E in terms of the natural base. It's E in terms of lowercase e, this side over here. All right, so E is equal to 8. All right, from here, we really just have two angles to find. And I'm going to start with angle D. And what I know is the given sides were 15 and 17. So I'm going to set this up this way. I'm going to say that the sine of D is equal to 15 seventeenths. And then we can do an inverse sine of 15 seventeenths. And we'll find angle D. Again, we're working in degrees. You should already have your calculator in that mode. But I'm getting that to be about 61.92 degrees. There are many ways you could find the other angle. One would be to do an inverse cosine of 15 seventeenths. You could also use this side E and use either the tangent or sine functions. There are probably other ways too, but perhaps the simplest would just be to say, well, we know the angles E and D have to sum to 90, and we just found D to be 61.92. And so I'll just use the number in my calculator and subtract it. And when I do that, I'm getting 28.08 degrees. Again, lots of ways to find, especially the angles, the side. You're pretty much locked into Pythagorean, I would think, unless you want to do something really crazy. All right, let's get into the application problems. The next two problems, 3 and 4, we kind of run into things that honestly, we've kind of seen them before. So I'm not going to spend a ton of time on these, but let's take a look at them. A safety regulation states that the maximum angle of elevation for a rescue ladder is 72 degrees. A fire department's longest ladder is 110 feet. What is the maximum rescue safety height? All right, I'm going to go ahead and sketch a right triangle on here. And I'm not going to worry about things being drawn to scale. That's really not important to us. It's just important that we have things labeled correctly. Now, angles of elevation, it says this word right here. Anytime you see angle of elevation or angle of depression, those are always, always, always compared to the x-axis. Okay, so I'm just going to say it's the angle with the x-axis. And I don't know if I even like that I said x-axis. Probably the horizontal side would be better. If you want to think of it as the x-axis, that's fine. All right, so horizontal rather than x-axis, probably a better way to say that. All right, so here we go. We know this angle of elevation, that's with the horizontal. It's 72 degrees. The length of the ladder is 110 feet, and we're trying to find the rescue height. That would be this height right here. Again, I just analyze the situation and say, well, I know this angle, I know the opposite, I know the hypotenuse, and by know the opposite, I mean that's what we're trying to find, I suppose. So I'm going to use the sine function. I'm going to say the sine of 72 degrees is h over 110, and then we just simply multiply, and I've got the height to be 104.62 feet. All right, on number 4, we've actually already seen a virtually identical problem. So again, I'm going to move fairly quickly through this one. It is a little bit of a complicated one, and I would argue it actually can get quite easier, simpler when we get to law of sines, law of cosines. This simplifies this problem to a pretty significant degree, but I want to look at it again just to make sure you're kind of with us on this. So what we know is we're driving and our angle of elevation is 1.9 degrees right here. We drive 15 miles. That gets us that far. And now our angle of elevation is 7.2 degrees. We want to know the height of the mountain. Okay, the other thing we need to actually use to be able to find this is I'm going to put a variable x right there that represents this length. It's essentially the horizontal length to the middle of the mountain, I suppose. And then we're going to use our tangent function. So I know that the tangent of 1.9 degrees is equal to h, which is our opposite, divided by the adjacent side, which would be x plus 15. I could actually solve this for h pretty quickly. H is equal to, and I'm just going to put x plus 15 in parentheses times the tangent of 1.9 degrees. And then I have another tangent set up over here. I know the tangent of 7.2 degrees is equal to h over x. Again, we can solve quickly for h, and it's x times the tangent of 72 degrees. Now, we've got two variables and we've got two equations. I'm going to skip just a little bit of work here to save some time, but what I find when I set these equal to each other and solve is that x is about 5.34 miles. Okay, now it didn't ask us for x though, it asked us to find h. So essentially what I just need to do is take that 5.34 and I'm going to multiply it by the tangent of 72 degrees, and what I get there is about 0.6748 miles, and maybe more appropriate for this one would be to put it in feet, and I've got it at about 3,563 feet. Now it doesn't say in the problem we have to change it to feet, so if you left it, rounded, to 3-4 digits in terms of miles, I can't say that that's wrong. I'm just trying to give you a measure that would make more sense for the way we actually measure the height of mountains. Again, I know I skipped some work over here in finding x. If you look back a few sections in chapter 4, you'll see virtually an identical problem, and so you can see more of the details there. Or just find the smart kid that's sitting close to you and ask them how you got it done. Oh yeah, and speaking of smart kids, how about this mistake? I wrote tangent of 72 instead of 7.2. So there goes my smart kid card. Anyway, you probably knew that already. Anyway, all right, let's go take a look at the next question. This is actually where we learn something new. It can carry a bit of a challenge. We're going to look at something called bearings, and we're going to look at two different types of bearings. The first we're going to look at is if you are on land or on water, so boats and cars. We'll look at one for air navigation in just a moment. But in surveying and navigation, directions are generally given in terms of bearings. They include like compass directions, essentially. A bearing measures the acute angle that a path or line of sight makes with a fixed north-south line. So you can see over here we have an example of north, 35 degrees east. In other words, it's 35 degrees east of north. All right, so we're going to use that kind of concept. And what's weird is we're used to reference angles going back to the x-axis, but with bearings, it's always going to either north or to south. So we kind of have to adjust our thinking, but the concept isn't too out there. It's just a slightly different way of looking at it. All right, here we have a cruise boat traveling from one island called Sandy Island to Turtle Island, but a storm prevents it from taking a direct pathway. So you can see that the boat travels due north, and so I'm going to kind of sketch the situation here. We're going to say the boat's traveling due north, so we have a vertical portion of the trip there for 5 hours, and then it travels north 51 degrees east, so that's something like this, where essentially if we were to extend this side right here, we would see that this angle right there is 51 degrees. And that's going for 6 hours. The boat travels at a constant speed of 30 knots. Just as a note, just another navigational piece of information, 1 knot means 1 nautical mile per hour. Okay, so if you want to know how long a nautical mile is, you can look that up. It's actually a little different than a mile. It's not horribly different, but it's definitely different. All right, what is the direct distance and bearing from Sandy Island to Turtle Island? In other words, we're looking for, and I'm going to put this in blue right here, that distance. So essentially we're saying down here is Sandy Island, up here is Turtle. We want to know the distance and the bearing between those two. Now here's one thing I'm going to suggest to you. Sometimes we need to get right triangles, right? So we're going to do that here. I'm going to go ahead and connect this to form a right angle over there, and we're going to use the information from inside there. So let's start marking down the stuff we know. We know that's 51 degrees. I know that has to be a right angle. We didn't use the time and the distances yet, or the speed. So traveling north for 5 hours at 30 knots means that this distance right here is 150 nautical miles. And then after the turn, it's 6 hours 6 hours, still at 30 knots. So this distance over here is 180, and again, that's measured in nautical miles. My handwriting's a little sloppy there. We'll try it again. Nautical miles in M, you can use that. And yeah, that'll work. All right, what is the direct distance and bearing? So here's what I'm going to suggest. In order for us to find the distance, okay, I'll just call that D right there, and the bearing, which means we're going to have to eventually find this angle right here. I actually need to use this little triangle we formed up here. I'm going to call this side X and this side Y. It doesn't matter what you call them, but we need variables there, because if we can find those two, we'll be able to use Pythagorean, and we'll be able to use some inverse trig. So here we go. I think what I would start with is by saying that the sine of 51 degrees is equal to opposite, which is Y, over 180 nautical miles. And so pretty quickly, just by multiplying by 180, we can see that Y is about 139. I'm going to go 2 decimal places here, but you could probably just leave it in your calculator. Okay, so I know the value for Y. I can also find the value for X if I do the cosine of 51 degrees. And again, there are other ways to do this, but I'm just rolling with the angle that's there, and it works pretty quickly. And then again, 180 times the cosine of 51, I'm getting 113.5 27.28 nautical miles. All right, so that is our x, that's our y. Now, why do we need that? Well, we can now find the distance because I know that d squared is equal to y squared plus, well, this side over here is x plus 150. I'm just going to write x plus 150 squared. Now, obviously, we know x and we know y, so we're just going to plug in those numbers. And I'm getting the distance to be about 298.13 nautical miles. Okay, that's one of the key things. That's the distance. And then it also says we need to find the bearing. Well, again, if I'm going to find the bearing, I need this angle right here. And look at this, I know y, I know this side. So basically, I'm just going to use a tangent function. I'm going to say tangent of theta is equal to y over x plus 150. Again, we know y, we know x. Those numbers are still in our calculator from back over here. And when you do an inverse tangent of those numbers, we get about 27.98 degrees. Now, if we're going to put this into a bearing, we would need to say, actually, not just the angle, but we need to say that we're traveling north 27.98 degrees east. In other words, we're going just about 28 degrees east of due north. Again, there's a little work on that one to get it set up, but one of the keys is we had to figure out where that right triangle was and work with it. So there's your intro to bearings. We have one more type we're going to look at now. We talked about how in land and sea navigation, everything is in terms of how far our angle is from either north or south. But for some reason, they use a little bit different type of measurement for bearings when it's air navigation, so airplanes. And theirs is actually a clockwise angle, but it starts at due north. So you can see an example here. This is 210 degrees. Now, if this were on land or sea, we would say, well, that's south 30 degrees west. But when it's air, we can just use the one number, 210, which means we're clockwise 210 degrees from due north. So you could go, I mean, if you were just 1 degree to the west of north, you would be 359 degrees. And then once you hit 360, you're actually back to zero, and you could start to scale over again. All right, so let's take a look at this. A jet leaves Reno and is headed toward Miami at a bearing of 100 degrees. So I'm going to start by kind of sketching this. It probably doesn't make sense to start trying to work on anything until I have a sketch. So we're going to put Reno up here, Miami's down here. All right, and go ahead and do a quick triangle situation here. Get that going. That'll work. There's our right angle. Again, this is Reno, and this is Miami. Now remember, when we say we're traveling at a bearing of 100 degrees, what that means, I'm going to extend this side just a little bit here, is that the angle that goes all the way from here to here is 100 degrees. Now what we need, though, is not that angle that's outside, but we actually need to use the angle that's inside, and we know that's 80 because those two are a linear pair. They're supplementary. They sum to 180, kids. All right, so the distance between the two cities is 2,472 miles. The question says, how far north and how far west is Reno relative to Miami? So essentially, I need to find this distance. That'll be how far north. And right here, that distance will represent the distance west. This problem, once we set it up, it's actually pretty straightforward. So I can just say, oh, the sine of 80 degrees is equal to W over 2472. So W would be equal to, let's see, 2,434. I'll just go to the nearest tenth. I think that's probably going to be enough accuracy for us. And then we could do something similar. We could do the cosine of 80 degrees is equal to our adjacent side divided by our hypotenuse. And we get our value for that side to be about 429.3 miles. So I'm going to go ahead and finish this with a somewhat complete sentence. Reno is about 2,434 miles west and 429 miles north of Miami. All right. Takes a while to write a sentence. I'm not good at this English stuff. All right. Last one. If the jet is to return directly home to Reno from Miami, those cities aren't moving, right? They're here and here. So we're going the opposite pathway. At what bearing should it travel? So here's what I'm going to do. I'm going to kind of sketch this. Some of you may actually may not even need to do this, but I'm going to draw this to represent due north. Okay. And then I'm going to grab a green marker here and show you what we're talking about is the angle right here. Okay, that angle. Well, we haven't actually calculated that angle, but we know a little piece of it, don't we? We know like this part right here has to be 10 degrees, and then the rest of it is 3/4 of the circle. So our angle is 280 degrees right there, and that is the bearing that we travel to go back on our trip. You might note that there's a bit of a relationship there between the bearing when we head from Reno to Miami and the trip back. It's probably worth investigating to see if that would hold true in other cases. So I hope these notes work for you. You will have some challenges on your assignment today. Be diligent with it. Do not quit at the first sign of trouble. Keep working hard. Ask questions of the friends and the other kids that you don't know their names that are sitting around you, and then bring other questions back to class. Next time we meet, we'll discuss them some more. Have a fabulous day.